In this video, we're going to be looking at the set of rational numbers. What we're going to be doing here in this particular video, we'll begin what Chapter 6 deals with is rational numbers and proportional reasoning. And the first section deals with the set of rational numbers. In this section, we're going to be looking at the equivalent or equal fractions, simplifying fractions, equality of fractions, ordering rational numbers, denseness of rational numbers. Okay, we'll look at the definition of what rational numbers are. It's a set of numbers called Q, such that Q is going to be the set of all numbers A divided by B, such that A and B are integers where B is not equal to 0. So usually rational numbers will be in the form of A over B. It's going to be in the form of a fraction. And in this fraction, A over B, the number on top, that's your numerator. The number on the bottom of the fraction bar is your denominator. Okay? So the numerator is always above the fraction bar. The denominator is below the fraction bar. And there are three uses of rational numbers here. So be very advised of these four uses of rational numbers. Rational numbers can be used as a division problem or a solution to a multiplication problem. Like in this case, 2x is equal to 3. It would be equal to 3 over 2. So 2x equals 3 would be the same as 3 over 2 as your x value, because that's the solution that will satisfy that equation. It can be used as a partition or part of a whole. Like in this case, Joe received 1/2 of Mary's salary each month for alimony. Okay, that's a partition or part of a whole amount. Rational numbers can be used as a ratio, where the ratio of Republicans to Democrats in the Senate is 3 to 5. And it also can be used as probability. When you toss a pair of coin, the probability of getting heads is 1/2. So these are the four different uses of rational numbers. Okay, and here are three different models for rational numbers. One of them is the area model. Here in this case, we got a four-sided figure that's divided into 3 equal parts, and one of those equal parts is shaded. In the middle, we have the number line model, where from 0 to this point is shaded and is sectioned into parts of 3. So we can say 2/3 of this is shaded. Also, we can think of this as a set model, where we have 5 circles. 3 of the 5 circles are shaded, so that's 3 out of 5, or 3/5. Okay, let's look at the meaning of a fraction. To understand the meaning of any fraction, A over B, using the parts to whole model, we must consider each of the following. And here are the 3 things that we must consider. One is the whole being considered. Number 2, the number, which is your denominator, of equal sized parts into which the whole is divided. Okay, because let's say, for example, the whole is going to be this circle. That's the whole that I'm considering. And then the B will be the equal sized parts in which that whole is going to be divided. So in other words, I'm going to take this whole circle and divide this into 4 equal parts, as you can see here. That represents the denominator. The number A, which is the third thing we must consider, the number A, or the numerator, of parts of the whole that we are selecting. So in this case here, if I select let's say 2 out of these 4 parts, here I'm shading 2 out of 4. Okay. So that would represent 2/4 or 1/2. And we'll talk about equivalent fractions a little bit later. Okay, let's look at what a proper fraction and an improper fraction is. A fraction a over b, where the absolute value of a is between 0 and the absolute value of b, is a proper fraction. And a couple of examples are 5/8 and -2/3 are proper fractions. Now, this definition may be a little bit vague, but let me explain this a little bit better. In a proper fraction, the numerator is always less than your denominator. So 5/8 is a proper fraction because the numerator of 5 is less than the denominator of 8. -2/3 is a proper fraction because if we disregard the negative sign, the numerator, which is 2, is less than the denominator of 3. Now, the improper fraction is defined as a fraction a over b such that the absolute value of b is less than 0, greater than 0, but less than or equal to the absolute value of a. In other words, you can think of this as the numerator being bigger than your denominator. Like 8/5 is a improper fraction because the larger number is bigger than the smaller number. The numerator is bigger than your denominator. 8 is bigger than 5. Also, -3/2 is an improper fraction because if we disregard the negative sign, the numerator 3 is bigger than the denominator of 2. Okay, so know the difference between a proper fraction and an improper fraction. Let's look at the number line model. In this case here, what numbers are represented on the number line? Okay, so here you're first given dots and you want to find out what numbers will be represented on this number line. If you look at it, from 0 to -2, this is section off into fourths. So this dot would represent -7/4. Okay, because -2 is the same as saying -8/4. Okay, so -8/4 is the same as -2, so the dot before it has to be -7/4. And the one before it is -6/4 or -3/2. Okay, and then we got -5/4 here, and then this dot will have to represent -1. Okay, and if this is 0 here in the center, then this dot right here to the left of that is -1/4. And then here you got 3/4 here, 1/4, 2/4, 3/4, and then 1 whole. And then for this last one, 5/4, 6/4, 7/4. Okay. So here those are the numbers that are represented by those dots on the number line. Let's look at equivalent fractions, or sometimes called equal fractions. Equivalent fractions are numbers that represent the same point on a number line. Let's take, for example, this representation of 1/3, where this box is shaded. One of the boxes is shaded out of 3, so that's 1/3. If we take each of these individual boxes and cut them in half, now we have 6 smaller boxes. In this case, 2 of the 6 smaller boxes are shaded. So 2/6 is an equivalent fraction of 1/3. Now we can go a little further by dividing each of the 6 boxes into 2 smaller boxes. So now we got 12 boxes. And here, 4 out of the 12 are shaded. So 4/12 is another equivalent fraction of 1/3. Okay, and what you see here are just some fraction strips that are used to help students, your elementary and middle school students, understand the concept of fractions and equivalent fractions, like in this case here 1/3 and 2/6 and 4/12. In this case here, if you take 4/12, that's the same as 1/3, and then 2 1/6 bars to represent 2/6 or 1/3 as well. Let's look at the fundamental law of fractions. Let's say we let A over B be any fraction and n a non-zero whole number. Then A over B is equal to A times n over B times n. That means I can multiply the numerator and the denominator by any non-zero whole number to come up with an equivalent fraction. Let's say 3/4. If I want an equivalent fraction of 3/4, what I'll do here is multiply the numerator and the denominator by some non-zero number. In this case, I'm going to multiply the numerator and the denominator by 5. If I do that, I'll have 3 times 5. That's going to give me 15. Divided by 4 times 5, that's 20. So 15/20 will be an equivalent fraction for 3/4. Look at this example here. Here you want to find a value for x such that 12 over 42 is equal to x over 210. Okay, now what they did was come up with an equivalent fraction for an equivalent fraction for 12 over 42 that has the same denominator of 210. Because in this case, if you multiply 42 times 5, you would get 210. So in this case here, they multiply the numerator and the denominator by 5. So here 12 times 5 will give you 60, and then 42 times 5 will give you 210, which is going to be the same as x over 210. Well, these denominators are the same, so that means that this value has to be the same as this value of x. So x is going to be equal to 60. Okay, let's look at simplifying fractions. A rational number a over b is in simplest form if b is greater than 0 and the greatest common divisor of a and b is equal to 1. That is, if a and b have no common factor greater than 1. Okay. If no common factor for a and b is greater than 1, then that means that that fraction a over b, or the rational number a over b, will be in simplest form. And we're going to look at some examples that deal with writing fractions in simplest form, if they're not already done so. Here in part A, you got 28ab squared divided by 42a squared b squared. Okay, now I'm going to go through this one with you so you can see how this is done. So now you got 28ab squared divided by 42a squared b squared. Okay, now I want to reduce 28 over 42. Now I'm going to do that by finding the largest number that can go into 28 and 42. And I believe in this case it's going to be 14. As I know 14 goes into 28 2 times, and I know 14 goes into 42 3 times. The a, I'm going to bring that over. I'm going to write b squared because I know the exponent tells me how many times b is used as a factor. In this case, that 2 tells me that b is going to be used as a factor 2 times, so I write b times b. The a squared, I'm going to write that as a times a, and then the b squared is b times b. So this is what my numerator and my denominator is going to look like. Now I'm going to divide out some terms here. I can divide out the 14. I can also divide out one of the a's. I can divide out this b along with this b, and then this b with another b in the denominator. So in this case here, the numerator, I'm left with just I'm left with just 2 divided by, and in my denominator I have 3a. So in simplest form, this will be 2 over 3a, which is exactly what they have here. Okay, now look at part B. We got a plus b quantity squared over 3a plus 3b. Now you're going to have to dig deep in your background of algebra to think about how we're going to simplify this. The a plus b quantity squared, that a plus b is used as a factor twice. So let's rewrite this as a plus b times a plus b. That's your numerator. The denominator is 3a plus 3b. In 3a plus 3b, there is a common factor in 3a and 3b. And that's going to be the 3. So I'm going to pull the 3 on the outside. And then I'm going to divide 3 into these two terms to get what's on the inside. So 3a divided by 3 is a, plus 3b divided by 3 is b. So I got a plus b times a plus b divided by 3 parentheses a plus b. Notice I can divide out one of the a plus b's. So I'll be left with, in the numerator, a plus b. The denominator, I'll have 3. So it'll be a plus b over 3. And they tell you as long as a plus b is not equal to 0, this will be your answer. So as long as a plus b doesn't give me a sum of 0, that means I can divide this out. Okay, let's look at part C. X squared plus x divided by x plus 1. In this case here, in the x squared and x, the common factor is x. So I'm going to pull out an x as my common factor. Now when I do x squared divided by x, that will give me the x, and that x goes on the inside. Then plus x divided by itself is 1. So I have x times the quantity x plus 1. And that's divided by x plus 1. And as long as this x plus 1 does not equal to 0, I can divide the x plus 1 out completely in the numerator and the denominator, and I'll be left with x. Okay, so that's the final answer right there, which will be x. Now, in this answer, they say where x is not equal to -1, because I would get a 0 in the denominator when you replace the x with -1. Now look at part D. We got 3 plus x squared divided by 3x squared. In this case here, there's nothing that I can, there are no common factors in the numerator, and I can't do anything with the 3x squared. So in this case here, this expression cannot be factored. Okay. Because this cannot be factored because there's no common factors that I can take out in the numerator and in the denominator and divide out. Okay, let's look at some additional examples here. Let's look at part E. Here we got 3 plus 3x squared divided by 3x squared. Okay, now let's look at the numerator, which is 3 plus 3x squared. There is a common factor in those two terms in the numerator. That's the 3. So 3 can come outside the parentheses. And then we're going to do this 3 divided by 3, which is 1, plus 3x squared divided by 3 would just be x squared. So this will be 1 plus x squared. all that's divided by 3x squared. Okay, now here's what we can do here. I got a 3 in the numerator and the denominator. Those terms can divide out, and I'll be left with 1 plus x squared in the numerator. The denominator, I'll just have x squared. Now this will be as far as I can go with that problem. I cannot cancel x squares because this x squared is not a factor. It's being added to 1. Okay, look at part F. We got a squared minus b squared divided by a minus b. And we want to reduce this in simplest form. Well, a squared minus b squared, if you recall, on one of the videos, is the differences of squares, which can be factored into this. One term is a plus b, the other term is a minus b. Okay, that's one of the differences of squares that was discussed on a previous video. So you do have to get familiar with the differences of squares and how the differences of squares is factored. And this is the way it's factored. A plus b times a minus b. That's divided by a minus b. Now, as long as a minus b is not equal to 0, I can divide those a minus b's out completely, and you'll just be left with just a plus b. Now, part G, we got a squared plus b squared divided by a plus b. Okay, unfortunately, we can't factor the sum of squares as we would with the differences of squares. This one's a little bit different. We can't factor the sum of 2 squares. So here, this cannot be simplified. This is already in simplest form. Okay. So do be familiar with how to do these type of problems here. Let's look at the equality of fractions. Let's say we want to show that 12 over 42 is equal to 10 over 35. There are two methods. There are some methods that we can show that one fraction is equivalent to another. You can simplify both fractions to the same simplest form, like 12 over 42 will reduce, well, if you break that up as a product of primes, you have 2 to the second times 3. 42 as a product of primes will be 2 times 3 times 7. And then divide out the 2's, you'll be left with a 2 in the numerator. Divide out the 3's, and you'll be left with a 7 in the denominator. So you have 2 over 7 as an equivalent fraction for 12 over 42 in simplest form. For 10 over 35, 10 is going to be 5 times 2. 35 is a product of primes, so it'll be 5 times 7. We can divide out the 5, so you'll be left with 2 over 7. So 10 over 35 will be equal to 2 sevenths in simplest form. So that's one way that you can show that one fraction is equivalent to another. Here's the second method. You can use the least common denominator to rewrite both the fractions. In this case, for 42 and 35, the least common multiple is 210. Now, if you're not familiar with finding the least common multiple, there is a video that I created that goes through how to find the least common multiple of two numbers. So for 42 and 35, that least common multiple is 210. And then we write an equivalent fraction for 12 over 42 with a denominator of 210. Here you have to multiply the numerator and the denominator by 5. So I'm going to put times 5 over here, over 5. So 5 times 12, that's 60, and 5 times 42 will be 210. Now for 10 over 35, to get 35 to have a denominator of 210, you have to multiply the numerator and the denominator by 6. 6 times 35 will give you the 210. 6 times 10 will be 60. So here those two equivalent fractions are the same. So we can say that 10 over 35 and 12 over 42 are equivalent to each other. And then the third method is to rewrite both fractions with a common denominator. So a common multiple of 42 and 35 is going to be 1470. This one's a little bit different because the one that I showed you, the second method, was using the least common multiple. This one, you're just using a common denominator and not the least common denominator necessarily. You just use a common denominator. They just took the denominators 42 and 35 and just multiplied them together to get 1470. And then to get this 42 to be 1470, you have to multiply the numerator and the denominator by 35. So the numerator will be 40 from the 12 times 35, and then 42 times 35 will be 1470. And then for 10 over 35, we have to multiply the numerator and the denominator by 42 in order to get the denominator of 1470. 10 times 42 would be 420. 35 times 42 would be 1470. So here again, you can see that the two fractions are the same. So that means that 12 over 42 is equivalent to 10 over 35. Okay. Here, two fractions a over b and c over d, where d is not equal to 0, are equal if and only if a times d is equal to b times c. In other words, we're going to look at what they call the cross products. That AD comes from the cross product here, and the BC comes from this cross product. So we're thinking of two fractions are going to be equal if and only if the cross products are equal. So if I go back to that last one, let's say 12 over 42, and I want to know if it's equivalent to 10 over 35, I can use the cross product method by doing 42 times 10. That's 420. And then do 12 times 35. That's going to be, let's see, 350 plus 70 is 420. You can see that these cross products are equal, so 12 over 42 is equivalent to 10 over 35. Okay, that's what we mean by using a cross products approach. Okay, now let's go on to ordering rational numbers. If a, b, and c are integers and b is greater than 0, then a over b is greater than c over b, if and only if a is bigger than c. If your denominators are the same, in other words, then the numerator of the first has to be bigger than the numerator of the second. Example. Let's say 12 sevenths and 5 sevenths. Here the denominators are the same, so we check the numerators here. 12 is bigger than 5, so 12 sevenths is greater than 5 sevenths. Okay. That's basically what that statement is saying. Okay, now if A, B, C, and D are integers and B is greater than 0, and D is greater than 0, then A over B is greater than C over D if and only if AD, which is this cross product here, is bigger than the cross product of B and C. Okay. So if we look at this one, 11 twelfths and 4 fifths, if we take the cross product of 11 and 5, you're going to get 55. If we take the cross product of 12 and 4, you're going to get 48. Compare this cross product to this cross product. That's 55, 48. 55 is greater than 48, so that means 11 twelfths is greater than 4 fifths. Okay, So also we can use the cross products to determine whether the the fraction on the left is less than or greater than the fraction on the right side. Okay, let's look at denseness of rational numbers. You're given rational numbers a over b and c over b, which means there is another rational number between these two numbers. Okay, so if you're given two fractions, we can find a rational number that is going to be between those two numbers. Okay, I'll give an example that has like fractions here. Let's see, 4/15, 7/15. Obviously, there is a number that's a rational number that's in between those. Like, we can say 5/15, which is 1/3. Or you can use 6/15, which is going to be 3/5. Okay. And here's an example of just that. You want to find two fractions between 7/18 and 1/2. Okay, we can write 1/2 with a common denominator of 18 by multiplying the numerator and the denominator by 9 to get 9/18. Okay, so here 8/18, or if you reduce it, it'll be 4/9. That's between 7/18 and 1/2. Okay, now you want to find two fractions that are equal to 7/18 and 1/2, but yet want greater denominators. Let's multiply the numerator and the denominator in 7/18 by 2. That would give you 14/36. And if I want a denominator of 36 for 1/2, multiply the numerator and the denominator by 18, so you'll have 18/36. Okay, now we can find two fractions that are in between 14/36 and 18/36. And here they are. 15/36, 16/36, and 17/36. They're between 14/36 and 18/36, so they must be between 7/18 and 1/2. Okay. Now show that the sequence 1/2, 2/3, 3/4, 4/5 is increasing. Let's look at the nth term of this sequence. It's going to be n over n plus 1. Now where do we get that from? Notice that the numerator is 1. The denominator is 1 more than the numerator. Okay? For 2/3 the same way. The denominator is 1 more than the numerator. Okay, and that's the consistent pattern for 3/4 and 4/5. So if we let n be that number, then the denominator is going to be 1 more than that, which is n plus 1. So that's why we have n over n plus 1. Which means the next term will have to be n plus 1 over n plus 2. Because if we increase this by 1, you get n plus 1. Increase the denominator by 1, you're going to have n plus 2. Okay, so we need to show that for all positive integers n plus 1 over n plus 2 is going to be greater than n over n plus 1. And it's going to be true if and only if, of course, n plus 1 times n minus 1 is greater than n times n plus 2. That's using the cross products approach. In this case here, n plus 1 times the n plus 1. That's this cross product. And then the other cross product, n plus 2 times n, is this. Okay? Now, take this, use the FOIL method. You're going to get n squared plus 2n plus 1 is greater than. The right side, you're going to use the distributive property. That will give you the n squared plus 2n. Which is, of course, going to be true for all n. So we can say that this sequence is increasing. Because this is, if you look at the left side and the right side here, n squared plus 2n and n squared plus 2n, that's the same. But if you add 1, this is 1 more than this. And for all n, the left side is going to be 1 more than what's on the right side. So the sequence would be increasing. Okay, now, the last thing we talk about is this. You want to let a over b and c over d be any rational numbers with positive denominators, where a over b is less than c over d. Then a over b is going to be less than a plus c over b plus d is less than cd. In other words, if you take the sum of the numerators and the sum of the denominators, you're going to come up with a fraction that's between a over b and c over d. Let me give you an example. 2/3 and 6/7. Now, if I do the cross products approach here, this will be 14 for 2 times 7, and this will be 18 for 3 times 6. 14 is less than 18, so 2/3 is less than 6/7. Okay? Now, I can come up with a fraction using this approach that's going to be between 2/3 and 6/7. If I add the 2 plus 6, my numerator is going to be 8. The denominator, if I add 3 plus 7, that's going to be 10. So here I got 8/10, which is going to reduce to 4/5. And 4/5 is bigger than 2/3, but less than 6 over 7. Okay, so this is what they call the density property, how you can use this particular approach of adding the numerators and then adding the denominators in your given fractions to come up with a fraction that's going to be in between those two given fractions. Okay, so that would conclude this particular section on the set of rational numbers.